Happy Monday, you guys. Today we are going to talk about the mole-volume relationship. Last week we learned how to relate the mass of a substance to the number of moles of that substance. And today we're going to learn how to relate the volume of a gas to the number of moles. So molar mass works really well when we can easily measure the mass of things, but it's kind of complicated when we're dealing with gases. We can't just plop them on a scale and find out their mass. Fortunately, there's a consistent, predictable relationship between the volume of a gas and the moles of that gas at a particular temperature and pressure. So that really comes in handy. So what is this relationship between moles and volume? What we have been able to establish is that at what we call standard temperature and pressure, I'll talk about what that is in a minute, at STP, 1 mole of gas, so 6.022 times 10 to the 23rd particles, occupies a volume of 22.4 liters. This number is sometimes called molar volume. And as long as you're at STP, this value is always true. The image of this little beach ball in the left corner is showing you about what the volume of 22.4 liters looks like. There's nothing else in the picture for scale, but it actually is really close to the size of kind of an average beach ball. And so, I don't know, I think that's kind of fun. Just to gain a perspective of what a mole of gas looks like. So this constant that I was talking about, the standard temperature and pressure, STP, is defined as being 0 degrees Celsius, so the freezing point of water, and 1 atmosphere. And 1 atmosphere is the average pressure at sea level. So the average atmospheric pressure at sea level. So under those conditions, 1 mole of gas is equal to 22.4 liters of gas. Now, that's a really specific set of conditions. And so later on in this class, we'll talk about how to study gases when they are not at STP. But for now, we're just going to assume that any gas that we're studying has been cooled to 0 degrees Celsius and is being kept at 1 atmosphere. And that allows us to use this conversion factor that 1 mole is 22.4 liters of gas. I want to walk you guys through a few examples of using the mole-volume relationship. This first example asks us to determine how many moles of carbon dioxide are in 84 liters of carbon dioxide. The second example asks what is the volume of 0.125 moles of nitrogen, so N2 gas. In example 1, we're going to start with what we're given. So we're starting with this 84.0 liters of CO2, and we'll use our conversion factor. We'll put our molar volume, 22.4 liters, on the bottom so that our liters cancel out. And then we'll have our 1 mole of CO2 on the top. Multiply the top, divide the bottom, and that gives us 3.75 moles of carbon dioxide gas. In the second example, we're going the other way. So we want to find the volume based on the number of moles. If we start with our 0.125 moles of nitrogen, we can use our conversion factor, and we know that 1 mole needs to be on the bottom, and that's so that our moles cancel out. We put our molar volume, 22.4 liters, on top, multiply it through, and we get that the volume is 2.8 liters. So hopefully As you've been becoming more and more familiar with factor label, this seems pretty straightforward. Here are two examples for you to practice. You should pause the slides and go ahead and give these a try in your notes. On the next slide, I will talk you through them. Okay, so the first question asks us about moles of neon gas in 56.9 liters. Start with what you're given, 56.9 liters, divided by 22.4 liters. And that gives us the 2.54 moles of neon. The next question asks us what's the volume of 3.2 moles of hydrogen gas. So we'll start with what we're given, 3.2 moles of hydrogen gas. Use our conversion factors. So divide by 1 mole of hydrogen gas times 22.4 liters of hydrogen. And that gives us 71.68 liters of hydrogen. I want to point out right now that this molar volume 22.4 is the same no matter how many elements are involved in the gas. So neon is a single atom, and its mole volume relationship is still 22.4 liters to 1 mole. Hydrogen is H2, and that's still 22.4 liters to 1 mole. Carbon dioxide, CO2, that is 3 atoms involved and 2 elements, and it still has the molar volume of 22.4. So I just wanted to point that out, that the type of gas does not matter when you are just considering the volume that the gas is occupying. If you wanted to find out the mass that the gas had, that would be a little bit more involved. And so we're going to do a couple examples like that as well. Okay, this is your best friend, the mole roadmap. Moles are really, really important in chemistry. On the back of your cheat sheet, you should have a copy of this roadmap. And this is super nice. It reminds us what our conversion factors are and what we can use to go through different transitions when we're factor labeling. Moles are in the middle because if you can get to moles, you can get to anything else. And that's really important to remember. So if you wanted to go from the volume of a gas to moles, you would use 1 mole over 22.4 liters. So now you're in moles. And if you wanted to then find the mass of that gas, you could use the molar mass. I think on your cheat sheet it says GFW, which is gram formula weight, which is pretty antiquated. People don't really use that anymore. So I need to update it, but I always forget. So if you want to cross out the GFW and write in the molar mass symbol, or if you just want to write a note next to it, like this means molar mass, please do. Yeah, so then now we can use our molar mass, which we calculate from the periodic table, to find the mass in grams of the gas that we started with back over here. Notice that there's no arrows connecting the volume directly to the grams, so we have to go through moles to get there. Similarly, if you started with the mass of a substance and you wanted to find out how many particles there were, you would need to take the mass, use the molar mass to get to moles, and then use Avogadro's number to get to particles. Okay, and so we'll do some examples of this guy as well, to get used to using it as a reference. If you do not find it helpful, of course you don't need to use it. I just wanted to present this information in a different way that's kind of visual, and hopefully it will help some of you and not confuse anybody too much. Okay, so if we want to use our mole roadmap, we will look at some more complicated problems. So this says, how many molecules of O2 gas occupy a volume of 39.2 liters? So if I'm looking at my mole roadmap, I'm like, okay, I'm looking for particles and I was given liters. So I'm going to need to use the molar volume constant to go from volume to moles, and then I can go from moles to particles using Avogadro's number. So that's my game plan for the first one. The second one says, how many atoms of sulfur dioxide gas occupy a volume of 56 liters? So if I go back, 56 liters, I'm going to start over here. I can go to moles, and then I'm looking for the mass, so I need to go to grams. And so I'll use the molar mass of sulfur dioxide to do that. Okay, so volume to moles to grams. That's my game plan for the second example. Here is example 3. How many grams of oxygen gas occupy a volume of 39.2 liters? I start with what I'm given. Oops. Just a second. Sorry about that, guys. There we go. 39.2 liters. I use my molar volume constant. So I have 22.4 liters of oxygen as a mole of oxygen. A mole of oxygen is 32 grams of oxygen. Molar mass, I pulled that straight from the periodic table. 16 plus 16, right, because I have 2 oxygens, is 32. So then I'll multiply the top and divide by the bottom, which gives me 56 grams of oxygen are in 39.2 liters. Example 4, how many molecules of sulfur dioxide occupy a volume of 56 liters? Again, start with what I'm given, 56 liters. So I'm going liters using my molar volume constant. 22.4 gives me 1 mole of sulfur dioxide. 1 mole of sulfur dioxide is Avogadro's number worth of molecules of sulfur dioxide. And so now I'm in molecules, and that's what I was asked for. So now I can go from 56 times 1 times Avogadro's number divided by 22.4 times 1, and that gives me 1.51 times 10 to the 24 molecules of sulfur dioxide. Something that we're going to get into a little bit next week is this idea that if you wanted to go to atoms, you would have to do one more step. If you wanted to know how many atoms were in 56 liters of sulfur dioxide gas. Right now we have molecules, and if we look at this molecule, in one molecule, there's 3 atoms of sulfur dioxide. And so if we wanted to know how many atoms there are, we would have to multiply this number of molecules by the number of atoms in one molecule. So we'd multiply by 3, and that would give us the number of atoms. And this question doesn't call for that, but that's something that I will ask you in the future. And so I wanted to go ahead and mention it now, and we'll look at some examples of that this week as well. All right, that is it. You have a practice worksheet that I have posted with this video. There is also a second set of slides that are a set of practice problems. I think there's like 7 maybe. And you should do those on a separate sheet of paper and turn those in as well. Normally we would do those ones like together in class as practice. And so I do want to be able to look those over and give you some feedback. And I'll post a key for them and for the practice worksheet on Tuesday. All right. Please let me know if you have questions. Thanks, you guys.